In this video, I'm going to talk about power series. I will define power series and give some examples and properties of power series. So let's go ahead and start off with a very simple example of power series, something you have seen before. So 1 plus x squared plus x cubed plus dot dot dot. This is a very simple example of power series, and this could be written in compact format, which is in summation notation. N is equal to 0 to infinity x to the power n. Now this power series has a domain of convergence. That means the set of values for which, a set of x values for which the power series converges, which you already know probably is absolute value of x is less than 1. That is to say that negative 1 is less than x is less than 1. That means x falls between negative 1 and positive 1. If the x values fall between negative 1 and positive 1, then this power series is going to converge. Okay. Now, on the other hand, if x is outside of this set of values, that means x is greater than or equal to 1 or x is less than or equal to negative 1, then this power series is gonna converge. By the way, this is a very special power series that you have seen before. Is the geometric series, right? So remember, our geometric series was summation n is equal to 0 to infinity, okay, is a r to the power n, right? Now here a is 1, in this particular example a is 1 and r is being replaced by x. Now I can take this example one step further. Let's introduce some coefficients to the left, okay? So then what am I gonna get? So I'm gonna get c sub 0 plus c1x plus c2x squared plus c3 x cubed plus dot dot dot. Okay, what does this become? This is nothing but summation n is equal to 0 to infinity c sub n x to the power n. Now this is a little bit more generalized definition of power series. Now if you look at the left hand side of this power series expansion or definition, is that it looks more like a polynomial, right? It's like a polynomial function, except that this polynomial function has infinite dimension, meaning that the power of x goes towards infinity. Again, when we are looking at power series, we are actually looking for not only the power series itself, but also the set of values or the domain of convergence, okay? The set of values for which the power series converges. So that is to say, we are looking for absolute value of x less than some real number, positive real number r, okay? If the x values fall within that radius, okay, the power series is gonna converge. Here, remember, r is positive, meaning r is greater than 0. So this is a slightly more advanced definition of power series. And the most general definition is going to be this. So C naught, okay, times x minus x naught to the power 0 plus C1 times x minus x naught to the power 1 plus C2 times x minus x naught to the power 2 plus dot dot dot, and that becomes equal to summation n is equal to 0 to infinity c sub n x minus x naught to the power n. Here again we are trying to find the set of x values for which the power series converges, or equivalently we are going to have something like this: x minus x naught, absolute value of it is less than r, okay? R is called the radius of convergence. Of course, r is greater than 0. That means it's a positive real number. And when we define a power series like this, we say that we are defining a power series, or we are expanding a power series about or at a point x naught, okay? About or at a point x naught, or x sub 0. Now, this is the most general definition of power series. This is something that we are going to be using a lot. And now what I'm going to do, I'm going to go ahead and talk about some properties of this power series. Again, the radius of convergence is something we are interested in, x minus x naught, absolute value of it is less than r, okay? Where r is a positive number. Now, once you know the radius of convergence for a power series, you know where this power series is going to converge. You can do a bunch of things with this power series, like as if you're dealing with a function. So for a regular function, let's say f, okay, let's say it's defined on a closed interval a comma b. So if this function is defined on this closed interval and it is continuous in this interval, you can do a bunch of things, right? You can take derivative of it, you can find integral of it, and all those things. You could do the exact same thing with a power series, by the way, all right? So if you have a region, or if you have a window where the power series converges, you could take let's define the power series first, okay? So our power series is going to be f of x, okay? Summation n is equal to 0 to infinity c sub n x minus x naught to the power n. So let's define this as a function, and then we're going to play around with this function. One thing I kind of want to mention about here is this. The special case when n is equal to 0. What does this do to us, to our power series? So it's going to be c sub 0 x minus x naught to the power 0, right? So this is a special case. What if x is equal to x naught? In that case, you have a situation 0 to the power 0, which is undefined, right? So in that case, we kind of assume that this is actually equal to 1. That's just an assumption, just so that we can be consistent with the rest of the terms in the power series. Now let's talk about taking derivative and finding integrals. You can treat a power series like a regular function in the domain where it converges, okay? So you could find the derivative of it. This is very important because there are functions for which if we take the derivative, or in some cases integral, it's easier to find the power series expression for it. As you will see, there are quite a few scenarios where derivatives or integrals of power series becomes important. Here I have written out the function, okay, so this power series. So my derivative of f of x is going to be f prime of x, right? Which is going to be taking derivative term by term on the right hand side. So derivative of a constant is 0, so I can just go ahead and ignore it. And the next one is going to be just c1. The next one is going to be 2 times c2 times x minus x naught. The next one is going to be 3 times c sub 3 x minus x naught whole square. And you can see the pattern here, right? And it keeps going. So I could really sum it up, summation n. So now look, my subscript changes here. N doesn't start at 0 really, n starts at 1. So it goes from 1 to infinity, c sub n x minus x naught to the power n minus 1. And then you multiply it by n right here, okay? So look, 3 times c sub 3, right? So n times c sub n times x minus x naught, the power has to be raised to 1 less, n minus 1, which is this. Now similarly, we can find integrals as well for this function. So let's find the integrals. So f of integral f of x dx, integrating with respect to x, and you can just do term by term integration. So it's going to give you c naught x, right, plus c1 times x minus x naught whole square over 2 plus c2 times x minus x naught or x sub 0 whole cube over 3 plus c3 times x minus x sub 0 to the power 4 over 4 plus dot dot dot. And then you can go ahead and use the summation notation here. Summation n is equal to 0 to infinity. So c sub n, okay, times x minus x sub 0 or x naught to the power n plus 1 divided by n plus 1. So I'm going to put the n plus 1 right underneath here. So n plus 1. And that should be your general term for integral. Now here is a slight technicality. I don't know if you noticed or paid attention to it. So I have c naught x here, right? So on the other hand, I put here x minus x naught, okay? Even for n is equal to 0. But remember, there is something we need to add here, which is the constant of integration. So this additional constant could be bundled into the total constant c here. So arbitrary constant c. So this is your integration of power series. So I have talked about the definition of power series. I talked about how to take derivative, how to take integral, as well as the set of x values for which the power series convergence or the radius of convergence. I hope that this discussion was helpful. Thank you very much.